Hi, and welcome to Physics 2211 Lab 5. The purpose of this lab is to predict the motion of a falling slinky using a computational model and comparing those results to real-world observations. Tracker was used to track the observed position of the bottom of the slinky, and GlowScript was used to create the computational model. The ultimate goal was then to determine whether or not the bottom of the slinky stays stationary in the model. When the computational model was created, it was found that the bottom of the model slinky remains stationary, so long as the top of the falling slinky hasn't reached the bottom. But first, let's start with some fundamental principles. Newton's second law states that the force is given by a change in momentum over a change in time. This can then be used to derive the velocity update and position update formulae. We will be using these formulae in our computational model very extensively. We will also use the spring force as shown here, which shows how the magnitude of the spring force is proportional to the stretch of the spring. We will also use the weight force, which is given by mass times acceleration due to gravity. For the tracker analysis, we used Derrick's height of 1.75 meters to calibrate distances. For the initial conditions, the top of the slinky was then defined as the origin. The initial velocity of the bottom of the spring was also set to 0 meters per second, and the initial mass of the spring was set to 0.2 kilograms. The data was taken from Tracker and plotted as shown in this graph here. Here, the bottom of the slinky remained mostly stationary until the top of the slinky fell down to the bottom. The bottom of the slinky then dropped under the influence of gravity. For the computational model, I modeled the slinky as a series of point masses connected by massless springs. In this code extract, I used 20 point masses to model the spring. I then initialized an array for the particles and their respective velocities. Initially, all the particles were set up equidistant from each other and with a velocity of 0. Then I allowed the system to equilibrate. This was done by calculating the net forces acting on each point mass and utilizing the position and velocity update formulae. Then for the main simulation loop, I had it such that the top of the slinky would be let go after 1 second. I would then loop through the entire array of particles and keep track of the spring forces acting on them from both the top and from the bottom. The net spring force was then added to the weight force to give the net force. This net force was then used to calculate acceleration. I then used the velocity and position update formulas to update the position of each point mass. This is a quick video which demonstrates how the computational model emulates real life. Here, the bottom of the slinky stays stationary whilst the top begins to fall down. This is a graph of the results from the computational model. Here, the bottom of the spring remains stationary over time. It then begins to accelerate downwards under the influence of gravity after roughly 1.5 seconds. For our discussion, we can say yes, the bottom of the model slinky does in fact stay stationary, just like in the video. This is because the bottom of the spring experiences an upwards force of tension and a downwards force of gravity that balance out. It takes time for the information of the falling slinky to propagate towards the bottom, hence why the bottom remains stationary. However, some sources of error include human error, with manually tracking the position of the bottom of the slinky. There may have also been some parallax error involved with the way the camera was set up. There were also assumptions made about the mass, spring constant, and the rest length of the slinky, which were used in the computational model, which could have led to some inaccuracies. We can now ask what would happen if a mass was attached to the bottom. In this case, the initial equilibrium state would be different. However, when the top of the slinky is released, the mass at the bottom will still remain stationary, as the spring force from above would cancel out with the weight force. We can also ask, what if the mass of our slinky was changed? Since our slinky is modeled as point masses with massless spring connectors, the more mass the slinky has, the greater the inertia of each spring segment, meaning it's slower to accelerate. Thus, it will take longer for tension to propagate throughout the entire spring. This can be seen in the graphs at the bottom, where with a mass of 0.03 kilograms, the model slinky remains stationary for around 1.25 seconds, whilst the slinky, which was 0.6 kilograms, remained stationary for nearly 2 seconds.